Welcome to Physics 2211 Lab 5 video by Michael Davis. In this lab, we will be discussing the motion of a falling slinky. In this video, we will be going over the purpose of the lab and also seeing a preview of the results. We will be discussing the fundamental principles, which are Newton's second law, gravitational force, force of a slinky, and the force of drag. We'll be going over some models, an observational model made with the tracker, and a computational model made with GlowScript. We'll be comparing and contrasting the data and come to a conclusion about our experiment. In this experiment, I decided to take a look back at previous experiments to see what the procedure I should take in analyzing this lab. I found lab 2, which was a motion of a falling object, to be the most useful lab. In that lab, we discussed Newton's second law, which includes the effect of gravity and the effect of drag. And I based my experiment and analysis off of this lab and the structure of lab 2. The fundamental principles we'll be using in this lab is again very similar to lab 2. We will be discussing Newton's second law, which is the change in velocity equals F net over m times change in time. And also that means that the F net equals each of our forces, which is the force of gravity, the force of drag, and the force of our slinky. Gravitational force discusses the weight force, the mass, and the Earth's gravitational force. And also it includes the direction of our force, which is straight down. Our drag force is our air resistance, and we discuss the object speed, the velocity's direction, as well as the calculation for it. And what this lab has that lab 2 didn't have is an additional tension force, which is our slinky force. So our slinky force starts as a tension force, but at a certain point in the video, it turns into an applied force. Using our data that we started with, like the mass is equals to 0.218 kilograms, our initial position, our initial velocity, and our time interval, I used the provided video to track the motion of a spring. The spring started in a stretched position where the man was holding it and the string was stretched all the way down. Once he let go, the bottom of the spring didn't actually move until the top of the spring fell all the way down to the bottom and then caused it to fall to the ground. This is because that the two things keeping it in motion or keeping it from moving are the force of tension and the force of gravity. And that force of tension turns into an applied force downwards as soon as it reaches the bottom of the spring. Here is a picture of a cat being picked up by tongs. This is just to make sure you're paying attention. If you are, leave a comment saying something nice about the cat. In the GlowScript code, I used the code from lab 2 to perform the experiment, to perform the analysis for this experiment. I plugged in the system's mass, the initial velocity and position, as well as our magnitude of acceleration, and also the proportionality constant, which I calculated through trial and error. For the second part of our code, which is our calculation loop, where we insert our forces and momentum principle, as well as the time intervals, we had to split our code into two different intervals, phase 1 and phase 2. On the left, phase 1 is where the slinky is stretched, and our two forces is the tension force and the force of gravity. These are the forces holding the bottom of the spring in place. And once the top of the spring reaches the bottom of the spring, that, like I said earlier, that tension force turns into a force downwards. And then the two forces that we are using is the force of drag and the force of gravity. I plugged in the equations for all of those forces into the code and ran the code. As we can see, we track the bottom of the spring, and it does not move until the top of the spring reaches it, and then the entire spring begins to fall downward. Comparing and contrasting the data, we can see our observed data in blue and our predicted data from our computational model in orange. Our observed motion is a little bit higher than the predicted motion, so the predicted motion reached the ground a little bit faster than the observed motion, and that could be because we did not account for all of the forces, or possibly our proportionality constant was not tested properly, or maybe I didn't even perform the tracker calculation properly as well. Coming to a conclusion about all of this, my hypothesis earlier was correct. The bottom of the spring did not move because the two forces were holding it in place, and until that top force, the tension force, turned into an applied force downwards, that is when the entire spring began to move to the ground. Thank you for watching. Goodbye.